The outline of my talk. Okay, got it. The outline looks something like this. The goal of my talk is to show you how I assess the quality of dipole sonic processing and interpretation. I want to start with some important concepts. Then we'll move into determining accurate slownesses in all formations, determine the magnitude and orientation of the anisotropy, which is commonly found in all of the Earth, and quantifying the different types of anisotropy and their cause. We'll look at two wells in particular here, the two forge wells that I've looked at, and I'll use that as an example. And then I'll come to some conclusions and certainly some recommendations on how I think this workflow should go. We hear the word integration quite a bit. I wondered what the dictionary would say about it, and they give two meanings, two definitions. One is kind of the social definition, incorporating society as being equal, and the other is the calculus definition. And so because it really didn't say what I think integration is, I created my own definition. And I think it's the synthesis or the bringing together of both multiscale and multidisciplinary data to solve complex multivariate problems. And I use the word complex in the sense that, you know, we don't totally understand the physics in many of the problems that we're struggling with today. They're certainly multivariate. There's many, many variables. And sometimes we're not even sure what variables we should be looking at to help solve the problem. So the reason we do the integration, I think, is certainly because of the synergy that you bring different pieces of data together and you develop a better insight into the problem and probably the solution. The workflow that I have followed is shown in this slide. I break it up into 4 activities. A knowledge activity, there's the geoscience activity. I think all the geoscientists are familiar with this. The engineering activity for design, this is like running your hydraulic fracture simulation and whatnot. Of course, you need the Earth model as an input into doing your simulations. And then there's the on-site activity to ensure that when you're out in the field that things go along as they're planned. But I want to highlight this knowledge activity because I think it's critically important. You start with what are the important issues? What are we really trying to do? There's the data audit where you collect the data. You take a subset of that data, for instance, the core data, and you'll do your geoscience analysis on it. You know, what's ground truth for porosity? What's ground truth for permeability? There's the engineering analysis as well, looking at all your in situ stress test and whatnot to really, you do this to build your calibration database. And in some sense, you build up a knowledge database. But this is critically important. And you do this first because this is really going to be how you judge your geoscience and how you judge your engineering. Does it make sense in terms of what I already know? So the Earth model that I think about looks something like this. There's all these disciplines, the large scale geology, geophysics, you know, your seismic data. In the blue boxes is the data that drives these components. You've got the borehole geology. We look at that to find breakouts and fractures. That helps us with the geomechanics. The geochemistry, a lot of that comes from core data. The petrophysical logs come into figuring out what's the mineralogy, what's the porosity, what are the fluids and whatnot. And I'll concentrate today on this borehole geophysics, you know, the dispersion analysis, 3D anisotropy, and finally, there's a good amount of rock physics that comes into this. And all of these disciplines need to be, I won't say completed, but certainly pretty far down the road before you can really get into the geomechanics and quantify the rock strength and the Earth's stresses. So we'll concentrate on this today because I think there's a number of things that geomechanical people need to understand about borehole geophysics prior to building their mechanical model. I've often heard it said that interpretation is an exercise in complication management. And when you start looking at the sonic tool, and it's no different than all the tools, there's so many complications that I had to break it into three categories. I have a tool related category. And a lot of these things, your transmitters and receivers need to be balanced. The transmitters, the two dipole transmitters have to transmit the same amount of energy. And you hope the vendor takes care of this, but I will tell you that sometimes they do and sometimes they don't. There's the environmental related complications. Many of these things are still outstanding problems. Borehole size and shape. Most of the algorithms kind of assume the tool is centered in the borehole and the borehole itself is circular. Well, we know it's not. And we don't often know what that does to the signal. There's mode contamination. Your mud properties vary as a function of depth. Doesn't really, a lot of the time it can be quite different than what's on the log header. You've got irregular tool motion. And this is all things you need to think about before you get to the interpretation. You need to think about anisotropy, invasion, fluids. Much of the rock around the borehole could be altered. There's a permeability effect on the Stoneleigh wave. So really, to bring the process data into geomechanics, it would be really good to understand from the person who processed the data, what were the complications that and how big were they? There's been a number of generations of sonic tools. The first sonic tool was called the borehole compensated sonic. It had two transmitters shown in green and 4 receivers, and they'd make a downgoing measurement of the speed of sound and an upgoing measurement, and they took the average of those two. This short spacing tool was often affected by the damage around the wellbore. So by the 1980s, they had decided that sonic tools need to be longer spacing. And so the second generation of sonic tools came out. The dipole tools were introduced in the early 1990s. I'm not showing every vendor here, but I'm showing, kind of how did the hardware, how did the software, change over time. And so array tools were introduced in about 1990. These are what I call third generation tools. And the sonic scanner, and now Halliburton has introduced the examiner imager, which is a recent tool that is very similar to the sonic scanner. These are 4th generation tools. So what have been the kind of differences? Well, 3rd generation, the tools are identified here. I call these third with a plus sign. They're not really 4th generation tools, but they're often better than 3rd generation. And then you've got the 4th generation tools. The differences typically in the electronics, the analog to digital conversion, the number of bits that we're able to capture today is quite a bit more than we did in the past. The transmitters are different over the different generations. The centralization is improved today, and then there's software as well. So there's 2 technologies that have been introduced. The original technology was what we call head waves. You have a source in the mud, and you broadcast a signal. There's a ray that goes here, and you get some internal reflection, and you get the body wave in the formation. And as this body wave propagates up the borehole, it drags behind it what we call a head wave. This is like a bow wave from a boat. And as that head wave crosses your receiver array, you can measure the velocity. This was how we started in the late 1950s. We could measure a compressional or P wave. And from about 1985, in a fast formation, you could measure a shear wave. But we weren't able to get a shear wave in slow formations. And so we got all excited about borehole modes. And so we've got monopole modes, we've got dipole modes in offshore or LWD environment. We go to quadrupole. And so today we process not only for the head waves, but for these borehole modes as well. So what's a borehole mode? Well, dipole transmitters cause the earth to vibrate. And so you can see kind of this borehole is vibrating back and forth. And this causes a pressure disturbance so that the hydrophones that we measure at the receiver array, when the borehole is moving to the right, we get a high pressure on the left and a low pressure on the right. And so we measure the pressure in the borehole, and we can determine two perpendicular shears. And when they're different, we can orient them. And the one that's faster, we call fast. And perpendicular to that should be a slow shear. The borehole modes are typically dispersive. And that's a problem. In processing waveforms, we use, the industry standard is slowness time coherence. This was introduced by Chris Kimball and Marzetta in 1984, but it doesn't really work on dispersive waveforms. Then dispersive slowness time coherence came out to try to deal with dispersion. And you can actually, if you have high fidelity waveforms, then you can determine slowness from the dispersion. But primarily, it's still the slowness time coherence that dominates the processing for shear data. So what is this dispersion? Well, it's the observation that the slowness that you measure is a function of frequency. And for a homogeneous and isotropic formation, it looks, like this red dash curve. There's two asymptotes that you see in this data. The low frequency asymptote is the shear slowness of the body wave in the formation, even though we're measuring the vibration of the borehole. And the high frequency slowness is known as the Schulte slowness. It's an interface wave between the liquid in the borehole and the formation. These modes, vibrational modes of the borehole, they have the greatest energy at about halfway between the shear and the Schulte. And I'm not really interested in this intermediate slowness. I really want to know what is this low frequency asymptote. But unfortunately, the amount of energy that is in the waveform at these low frequencies is pretty small. So, you typically have a usable bandwidth, and down here, it's just, you don't measure anything because it's too low in energy. And so the technique for this, and this was common in all your third generation tools, was to take all these high frequencies and filter them out. And essentially process where you have a little bit of energy, but there's a bias that what you process, you get something that's too slow because you don't have enough excitation down here in these lowest frequencies. And so this was known as a bias correction. And the correction that was made was based on the assumption that every formation is homogeneous and isotropic. We know, however, that if you have damage around the wellbore, say it's a breakout or a drilling induced fracture, this damage causes the increase in slowness. The speed of sound slows down. We call it damage, and the bias correction based on an HI formation is not large enough. But if you get into shales, most of them are what we call VTI, and a VTI formation, the bias correction will be too large. So that is the problem with your third generation of tools. So this was solved in the fourth generation of tools by creating a wide band transmitter. You want your dipole transmitter to put out a lot higher energy in the low frequencies, and you want a fairly flat response over a wide range of frequencies. So with third generation tools, you really had to do a bias correction, and it was never correct. So that's why these fourth generation tools went to a chirp drive. So it's like vibrosize in the sense that over a short period of time, you excite the formation with high frequency, and then you end up with lower frequencies. And this prevents the problem of having to decide before you log the well whether you're going to go with a standard dipole source or a low frequency source. And then you kind of had to know the answer before you even got started. And it was a big function of hole diameter. So this really kind of solved the problem. Today, I'll be talking about the Nevada Forge site in Nevada. And we'll look at the 2131 well. We'll also be looking at the 5832 well that is in the Utah area. So the Nevada was logged with the fourth generation sonic scanner. The Utah Forge site was logged with the third generation Schlumberger's dipole sonic imager, the DSI tool. So I created a displays that you always want to look at the waveforms. So here's your Stoneleigh, here's your PNS wave, your high frequency monopole, here's your dipole data. And you can see that at low frequency, the red dipole and the blue dipole, you can see that it asymptotes to that shear slowness. And this is the beauty of that chirp drive. Whereas in third generation tools, you really don't have enough energy down here at these low frequencies for it to asymptote and flatline, and so you're left with doing a bias correction that, depending on what kind of formation you have, in general you're not going to be as accurate. When we look at dipole, then this is the particle motion around the wellbore. It's helpful if I put in some lines that if you pop the east-west dipole here, you can see you've got a strong amplitude in the east-west direction, but no energy is on the cross-line component, which is right here. So if your dipole, if you're measuring this particle motion, you go from maximum amplitude east-west, and as you get to the cross line, it'll go to 0. So the dipole component is really the difference in pressure between hydrophone 5 and hydrophone 1. So you end up with 4 dipole measurements. So when you look at let's take a situation where I've got a set of parallel fractures shown in blue lines. And let's say that my blue dipole, my X dipole is aligned with the anisotropy, aligned with the fractures, and my Y dipole in red is perpendicular to the fractures. So, and let's say that I slow down because of the fractures by 20%, 120 microseconds per foot in this direction, and aligned with the fractures, let's say it's 100. So what you expect is on your X dipole inline that you have a high energy, much like we saw in this animation. The cross line would be 0, and the Y dipole inline, again, it would be high, and the Y dipole cross line would be 0. But the problem is the tool is rotating as you come out of the borehole. So your dipoles are never going to be, well, they're going to be aligned with the anisotropy at some point. And but with the tool turning, you have to deal with this. So the way we deal with it is if your dipoles are not aligned with your fractures, then you end up not having a high energy on the inline component, and you don't have zero energy on the cross line. So you get kind of medium energy. So depending on what we call this rotation angle, my Y dipole, let's say, is at 0 degrees. My X dipole on the tool is perpendicular, it's at 90 degrees. So I measure this medium amount of energy on my X dipole. I measure a medium amount of energy on the cross line component for both the Y dipole. But the direction of the anisotropy, I've got a minimum in energy on the cross line here, and I got a minimum in energy right here, and one turns out to be fast and one turns out to be slow. How do we know? Well, this rotation angle is just a coordinate transformation. And so if you rotate the inline and cross line, these four components from the Y dipole, then you can synthesize the waveforms at every angle that the tool might be pointed. And you can see that if I rotate to about 55 degrees here, I'm going to have a minimum in cross-line energy. Here's another one. This comes from the dependence on energy with azimuth. And so what we do is like I put in this purple line, and I know this is fast because the first arrival comes in sooner than what it does here. So you have to add additional information to determine, whether this minimum and cross-line energy corresponds to the fast wave or to the slow wave. And then I can take this rotation angle and add it to the direction that my dipole is pointed, or the tool orientation, and determine what is my fast shear azimuth. And that gives me information as to the strike of the fractures or the direction of the present day stress field, depending on what's dominating the anisotropy. So I had to make a new diagnostic plot because I would see data that was inconsistent with what I would see in an image versus what we knew about the geology. So in this plot, I take the two dipoles. The X dipole is in blue, the Y dipole is in red. And because the transmitters are not co-located, they're about a foot different, then the only co-located waveforms I have are a subset of, I've got on the sonic scanner, I've got 13 waveforms. So there's 11 that I can use for the four component analysis. And you can see that the two dipoles are in phase. If you look at the cross-line component, you see that I do have some energy on the cross-line. It's not zero. And here I look at the X dipole, both the inline and the offline, to see that they're in phase. And here's the Y dipole, both inline and offline, and I superimpose them here. And so this is very high quality data. I've got the dispersion analysis here, and I want to blow this up on the next slide and show you. So the standard way that we determine the direction of the anisotropy is plotting the energy as a function of this rotation angle. And if I blow it up, I find a minimum in energy right here at 55 degrees. And if I go and rotate from 0 to 180, I find another minimum here at 160. And so I try to fit this with it's essentially a 4 theta sine wave in 360 degrees, or a 2 theta sine wave in 180. And the model doesn't match the data very well, primarily because the minimum and energy are not 90 degrees apart like the assumption of this model would have. So the alternative method that I began doing, and I want to give credit with Charles Neville, he's on the call today. They were doing this in the early 1990s, even with third generation sonic tools. So what we do, and we call this the rotation scan method, is we rotate the waveforms just like we've always been doing, but we do it 36 times. We do it every 5 degrees from 0 degrees to 180 degrees. So those are the red dots that you see here. And then we just stack the waveforms. We compute slowness time coherence, but we do it 36 times. And we fit this this angle, this rotation angle data with a single theta sine wave. And you can see the black, that's the goodness of fit. So in this particular depth, you know, there's some inconsistency. The minimum energy occurs at this slowness, which this would be your fast. So the blue line shows you the trough of the sine wave, and the blue line here shows you the peak of the sine wave. So this is your slow shear, and this is your fast shear if you believe slowness time coherence, and we do. But in this particular case, the minimum in energy does not correspond to the single sine wave here. So you look at what's going on, and what you find is, even though there's, you know, in this example, very little anisotropy, there's only 0.6%. For one, it's measurable, and there's this ambiguity in the fast shear azimuth. The rotation scan finds more anisotropy than the minimum cross-line energy criteria. This is what we find in general. So the minimum energy technique assumes the formation is homogeneous from the transmitter to the receiver, which is often, you know, more than 10 feet. Whereas this rotation scan technique assumes the formation is only homogeneous across the receiver array, which is only 3 feet. So I believe that this technique is very strong and often gives better answers than the minimum energy. So if we look at the Nevada Forge data, here's an interval that you can see is highly fractured, and you can see the dip and azimuth of these open natural fractures shown in blue. You know, sometimes they're dipping off to the west or a little bit south of west. Sometimes they're dipping to the southeast. So it's a very complicated. It's not a single set of planar fractures, which also these methods assume. So you look at the diagnostic in this data, and again, I'm looking at the inline and cross-line components, and you can see some noise on the waveforms. This is typically due to the centralization calipers rubbing on the borehole wall, making some noise and whatnot, and you're not really in phase in some of the offline data, but and again, you even when you have large amount of anisotropy, you know, here we're, you know, 94 microseconds per foot for the slow, and we're up here around 102. So your minimum and cross-line energy, they're not really 90 degrees apart, and you've got a terrible fit to the, you know, to the model, but the numbers are fairly close. And here's another depth that shows what I often see is that these two techniques, the rotation scan technique, which is kind of a brute force just rotate the data 36 times, and you compare it to the minimum cross-line energy. I think the reason is because we have such a complicated wave field due to all of the different geometries that we see in these fractures. So if we look at this information as a function of depth, the minimum energy technique gives this percentage of shear anisotropy from 0 to 25. Here's 15% anisotropy. We look down here, and like I say, most often this rotation scan finds more anisotropy than what we do with this minimum energy. And in blue is the rotation scan, fast shear azimuth. And if you believe the minimum energy, it's shown here in red. So a lot of the time it gives you something very similar. Some of the time it gives you something quite a bit different. So I want to move on and say, well, how can we better determine what's going on? And I have to introduce the shear from the Stoneleigh. It gives you the shear modulus in a plane that's perpendicular to the borehole. And you can compare this shear with the fast and slow shear to give you a fully 3D view of what's going on in your anisotropy. So the tool measures this delta T Stoneleigh, and it's if you remember the Pythagorean theorem, the Stoneleigh is on this side of the triangle. So it's a function of your delta T mud, and it's a function of the shear that's in the horizontal plane to the borehole, and modified by a ratio of the mud density to the formation density. But you can measure the Stoneleigh, and if you input a reasonable delta T mud and some densities, then you can invert for the horizontal shear, and that allows you to compare the shear velocity in 3 dimensions. So if they're all the same, then you would say, okay, I'm isotropic. And I color code this green in my anisotropy classification. If your anisotropy is due to layering, you'll find that there's no shear wave splitting. The fast and the slow, or those two, any direction is the same, but you find the horizontal stiffness is quite large. And so the big difference is because of the layering. And so I code this yellow, and this is classical transverse isotropy with a vertical axis of symmetry. But what I just showed in fractured granites and geothermal, that this is what you're dealing with. You hope to have fractures, and in fact, what we see in the Nevada data, they're not a single set of planar fractures. They're kind of all over the place. But this does give rise to some amount of shear wave splitting. And if you're pure HTI with a single set of fractures, then the Stoneleigh ought to be the same as the slow. When we go to mini rocks, we find all three are different, and we would call this orthotropic. But what I tend to do is I take the average of the fast and slow, and if the horizontal is greater, I say it looks a lot like VTI. It looks a lot like this, except for the shear wave splitting. So I would take this depth level, code it red, but I would invert for elastic moduli, assuming a VTI model. And the same way for if it's if the Stoneleigh is less than the average, this is typically a permeability effect. And then I say that's HTI-like. Dispersion analysis allows us to confirm this classification. So if we're isotropic, your two dipoles overlay, and you have a Stoneleigh dispersion up here. If you're VTI, then quite often you lose this increase in slowness with frequency. It becomes very flat, and the Stoneleigh becomes very fast. So this is really easy to diagnose just by looking at the dispersion. If you're in this fractured HTI, then you get shear wave splitting. You see it constant typically over a range of frequencies, and you tend to get a Stoneleigh that's slower than if it were not fractured. And this is the what we would call the permeability effect that we see, which is a function of frequency itself. And in fact, it's very large at low frequency, and you can't see it at high frequency. And then if you're stress-induced anisotropy, you get this classic crossover and dispersion, and the Stoneleigh looks the same as it does like in an isotropic. So what does all of this mean in terms of rock behavior and geomechanics? Well, when I see a typical brittle stress strain curve, I show you one here in red. Your concave upwards, I call this region 1. You've got a linear region, I call that region 2. You measure an elastic limit or a yield strength, and you begin concave downwards. You reach the peak strength of the sample, and of course you're in failure at that point. This paper by Halbauer looked at thin sections and showed you that as you go beyond the elastic limit, you begin to create microcracks in the sample, and they begin to coalesce, and you can even see after failure, you can even see the failure plane that was created as you loaded the sample. And then there's some residual behavior in region 4. Well, one of the important questions in geomechanics is to say, well, what are my in situ stresses with respect to this mechanical behavior? And so what I like to do is to estimate what these in situ stresses are with respect to my peak strength. And if I'm in region 2 and the yield strength as a function of peak strength is, typically about 0.7 or 0.8, then I'm in the elastic domain, and your linear elastic equations are fundamentally correct. Whereas if your in situ stresses are up here very close to the peak strength, it's as Mark Zoback says, that much of the Earth's crust is at a state of failure, and a failure model such as Moore Coulomb would be more appropriate. And of course, if you get in region 3, you're left with, an elastic model is not going to be accurate because my rock is not behaving according to my elastic constants, and so something needs to be done. So in region 2, you use the appropriate stress model. If your sonic tool says you're isotropic, then the standard poroelastic horizontal strain model is appropriate. If you're dominated by layering, then vertical and horizontal moduli are the key ingredients to estimating your minimum horizontal stress. However, and this is often ignored, if you read the literature or current papers even, they apply this model even when you have shear wave splitting. And you shouldn't do that. In fact, what is more appropriate, I think, is to use what we call linear slip theory. If the source of if the velocities are being affected by the fractures, then you can look at the background compliance and the fracture compliance and use these elastic moduli in your horizontal stress equation to get to model this this correctly. As I mentioned, Mark Zoback came up with the stress polygon in 1986. That was that was before we even had dipole tools, and what we find is the maximum horizontal stress plotted as a function of the minimum needs to be above this 45-degree line simply by the definition. So the stress combination between max and min needs to be on the inside of this stress polygon. If you're over here on the edge, then you're at a state of failure, and this would be the normal faulting failure. Here your strike slip, and here your thrust faulting. But if you come back to this brittle behavior, then you can use this elastic limit and say, okay, everything in this green polygon should follow the rules of linear elasticity. And of course, if I'm critically stressed, then more Coulomb, given here, gives me a good estimate of stress. Not a linear elastic model, but simply a failure model. And so if your maximum horizontal stress is here, you're at and minimum would be here, you're at a state of failure. And of course, there's this region in between, which is region 3, and you need to deal with this one appropriately. So when you start coding, am I linear elastic? Am I elastoplastic, or am I critically stressed? Then you look at the Niobrara here in the Denver Basin, and you begin to see, and I think this is one reason these unconventionals work, is because a lot of the rock is critically stressed. So you have these microcracks that I think are extended and grown with the hydraulic stimulation, and but yet you'll see in the literature that people assume this linear elastic model shown in red is valid everywhere. And here I've calibrated to a DFIT, both the Moore Coulomb failure model and the linear elastic model. And this stress barrier you see here between the top of the Nio and the Sharon Springs is a result of ductile behavior. Your linear elastic model is no longer appropriate. So in conclusion, borehole modes are dispersive. Third generation tools cannot accurately correct for dispersion. So fourth generation tools, because they use a broadband drive to excite those lowest frequencies, they're critical to getting the accurate slownesses. The minimum crossline energy method is what the industry has been using, for the last 30 years. It requires a homogeneous formation between the transmitter and receiver. In fractured granite, you're never going to see that. Your hydrophones have to be matched, and there's 104 of them in the tool. So, and this is not always true. Your shaker, your dipole transmitters have to be matched. The rotation scan method restricts the homogeneous formation assumption to just what's in front of the array. It does not require matched hydrophone response or transmitters. And so you compute a slowness slightly different, and I think your fast shear azimuth is more accurate. So my recommendations would simply be this: avoid the use of third generation tools. You can't get an accurate slowness with them. The fourth generation tools are better in terms of electronics, better centralization, better software. There's more we can do with the data. Expert dipole sonic waveform processing is required to use sonic results in field development decisions. Thoroughly evaluate the dispersion in the sonic data, understand the components in the waveforms, filter appropriately, always compute the 3 shear moduli, and diagnose the type of anisotropy. Compute both methods for fast shear azimuth, and finally use an appropriate stress model based on the mechanical behavior and formation anisotropy. So those are kind of some highlights in how we can best use all of this dipole and Stoney data to understand the rock, and then you're in a better position to do your geomechanics. I'd like to acknowledge the U.S. Department of Energy, both the Utah and Nevada Forge programs, Charles Neville with IFP in Paris, and the Borehole Image Specialist Group in Denver, Roger Reinmiller, Ron Parker, and Dan Martin contributed and worked with me on picking the dips and the features in the wellbore images. So with that, I would like to see if there's any questions.
Thanks, Tom. Tremendous presentation, really provocative. And I know we do have some questions here. So I don't know whether you can pull up the chat or whether it might be better because some of these are long.
Oh, let's see. How do I get to?
Well, if not, I can channel these presentations. So Professor Solomon added to one of your comments that the long-spaced sonic tool was also driven by the need to measure or calculate stress magnitude because of the introduction of horizontal wells.
Right. You know, most of this talk was focused on vertical wells. When you go to horizontal wells, things become very complicated, and so that's beyond the scope of this talk for sure. But certainly the motivation for the original motivation in the late 70s was because the seismic velocities and you know, the check shot surveys they do using the integration of the P wave velocity from the BHC was often slower than the seismic velocity from the check shot. And so the thought was it's the mechanical damage around the wellbore. And so if we increase the spacing, we can get a deeper depth of investigation and be a little bit more accurate. But the spacing between the two receivers was still 2 foot, and so you had an aliasing problem, and that very quickly gave rise to an array tool where the receiver spacing was 6 inches rather than 2 feet. And virtually everything since that time has been an array tool with receivers not more than 6 inches apart.
Yeah. Ali Danashi makes an observation. The fact that you have natural fractures in the formation indicates that the rock has been stressed beyond its maximum level, and you need to consider the behavior of the failed rock.
That's correct. Which is essentially the point that I'm making. The point that I'm making here is we know how to do this. We take the 3 stresses, the minimum, the maximum, and the vertical stress, and try to infer, you know, rotate into what you think the failure plane is going to be. So we need the friction angle, and compute where we are on the stress strain curve, and quite often we find many formations are critically stressed, which is what we see here. And in those cases, you're absolutely correct. This linear elastic theory is inappropriate, and we need to be using, you know, this critically stressed. And now it's the friction angle and perhaps the compressive strength that governs the stress in the earth, and elastic properties at that point are irrelevant.
Now the next question is from Ed, and I presume that's Ed Sieberts. A great presentation, Tom. He's acknowledging that considerable development has occurred over many years. To what extent does commercial, oh my goodness, I should know what this means. Ed, why don't you chirp in and express your question?
Hi, everybody. Yeah, SW's software.
Oh, geez, okay.
I'm just curious to what extent commercial software, you know, properly takes account of many of these scenarios that you discussed today. I mean, it's clear that there's considerable, let's say, science behind it all.
Yeah, these complications, I think we're still struggling. That was kind of at the beginning of the talk. I think there's a lot of work that needs to go on with borehole size and shape. Very little has been done with excentering. I think it happens quite often, not so much in vertical wells, although you see the effects of what I think is excentering. It's especially a problem in horizontal wells. Another complication is we're not measuring the velocity of the mud. And it varies, drillers often put an 18-pound per gallon pill at the bottom of the hole, and the rest in the log header says the weight of the mud is 14 pounds per gallon. And there's gas influxes, and so this can detract from your Stoneleigh interpretation. There's tool pulling, and this is a big problem in the Eagle Ford, in different places. So a lot of these complications that occur because of the environment are not very well studied. I mean, there's been some studies that have been done that show the effect, but there's no correction. There's no quantifying. It's like we need to measure the mud slowness and then use that in the interpretation, but we don't do that because we don't have a mud sensor on any of the tools. So Eddie, you're absolutely right. Some of this has been studied. We know, like in case toll, we know how the casing in the cement, can affect the slownesses, and that's all good. But yet we don't take that into account whenever we're quantifying for anisotropy, for instance. And this is, and I might add, this is why I think you still need an expert processor to be involved in this, not only to to cross-check, double-check that there's no tool-related problems, but to identify to the geomechanics people what were the complications that go on, and where are my velocities and my interpretation highly accurate, and where are they compromised, and just how big is the compromise on that.
So Tom, the next question is from Alexei Savitsky, and Alexei, I'm suggesting that you just unmute and ask the question.
Sure, thank you, John. Well, the question is, it's a traditional question. When we look at the equations for calculating stresses, you had a slide on this, and in a traditional workflows, people typically take dynamic properties and then correct them for static properties to get Poisson ratio, Young modulus for anisotropic system, anisotropic stiffness and Poisson ratio. But in a triaxial cell that you showed, the apparent linear slope during elastic regime. So it's not quite elastic, because we all know that if you unload, and we have unloading loops and cycles during this elastic region too, the slope will be quite steeper.
Absolutely.
Which indicates that we never have linear elastic response here in triaxial tests. We only have it when we unload the sample, and that's where we get this high stiffness. So I had two questions. So first question was, what do you think about the practice of correcting dynamic properties to static properties, when by static people consider this loading linear slope, which actually is not elastic? That's the first question. And second question is whether it's what would be your preference? So if you were to feed elastic properties into those equations, would you take from the lab unloading or loading elastic properties?
So no, I agree with what you're saying. And when you're in region 2, if your in situ stresses are in say region 2, then my recommendation would be to take the from your core data, take the best static value, and you can either convert from dynamic to static using I like to quantify the CIJs and look at Thompson parameters. And what I find is because Thompson parameters are ratios of slownesses or velocities, that they are more independent of this dynamic to static, simply because it kind of cancels out. But if you're in this low in situ stress compared to the rock strength, then my recommendation to people is use the elastic model. I think it's appropriate. Where I think the industry falls down is they tend to use these elastic models everywhere, whether you're critically stressed or not. And I think this is inappropriate, and we need to do better. That whenever we get to places where we think we are critically stressed and we think our in situ stresses are up here around peak strength, then I think Mark Zobek is entirely correct that you're on the edge of the stress polygon, and a failure model. You don't have to use more Coulomb. In fact, you could go to Mogi Coulomb, you could go to Drucker-Prager, you could use your whatever, and get a better estimate of the stress. And I think, in many of our critically stressed formations, they're very interesting to us, but yet you look at the literature and you see people still, applying this kind of model everywhere. And even when I think it's inappropriate. So yeah, dynamic to static, if you're in the elastic domain, then certainly we want the static properties. We've got the issue of scale that I didn't really highlight here, that your core data is, typically from very small samples. And I love core data, I would take that, but the mechanical behavior of, let's say, a geothermal project where, we're talking about a much larger scale than your core data, is the compliance of the rock at a larger scale the same thing as core? And we know that we've got to put that on a log plot. Fracture compliance is a function of scale. You span 6 orders of magnitude. And I think Laura Parak-Nolte has got some upscaling, some great work done on that to look at even flow as a function of fracture compliance. And she addresses the scale issues. So I agree with your comments. Static dynamic, the unloading is probably more appropriate than the loading, and that's something that you should discuss with a vendor that's doing your core work.
Thank you.
We're running.
Can I ask a question, Tom? Regarding the behavior, since realizing that the rock is in the failed state, what is your thought about possibility of any at a specific location, stop the tool, continue the measurement, increase the pressure inside the wellbore to stress the rock, and then release the pressure to unstress the rock and look at the difference and try to use the local modulus of loading and unloading in order to make your calculations? What are your thoughts about this?
Okay, good luck on convincing a driller to do that. I think that'd be a fantastic experiment. We had talked about, having some pretty sophisticated wireline logging strings with the MDT, and make some measurements where we could stop the tool in the hole, isolate a section, and do that sort of thing. And you wouldn't be relying on the driller to, that's kind of hard to do in the drilling domain. And I doubt you could convince them to do that. But on the other hand, I think it would give good information. One of the things that excites me is the distributed strain sensing from fiber optic. And I think that, historically, when we calibrate, we have some in situ measurement, and, we adjust the strains so that our model matches our defits, for instance, that having an independent measurement of strain, even if it's only vertical or only horizontal, I think is important, is going to add a lot of understanding in the future.
So we're running out of running out of time here. So I'm gonna Gong. I'm gonna skip over you. I'm sorry. You can send your question directly to Tom, and I'd like Tony Addis to have the last word. Tony, do you want to unmute yourself and ask your question?
Oh, thanks. Yeah, Tom, I love the presentation. I've been looking for this sort of breakdown of how sonic logs are processed to really understand it, and it's evaded me for some time. The reason is that I've seen a number of cases where, when I've had as received sonic data, when I plug that into the Poisson's ratio calculation, the Poisson's ratios, and I think these are typically with dipole type tools, the Poisson's ratio shows no relationship to the lithology contrast whatsoever. It's almost like a straight line. So does what you're saying about the third generation tool and this difficulty of establishing this lower bound shear wave velocity, is that the reason why I'm getting this insensitivity when I calculate the Poisson's ratio?
Okay, so in this paper, if you look at Poisson's ratio, typically in a carbonate, it's, what are we, 0 to 5. So 1, 2, 3, 4. Yeah, 0.25. And in the totally different lithology, you're also, 0.25.
Yeah, that's exactly the sort of thing I've been seeing time and time again.
Well, exactly. And so whenever you look at this, the friction angle up here in the clay, because you've got so much clay, and by the way, you got kerogen up there as well. That's the purple stuff. You get a very low friction angle, and Moore-Coulomb says that the vertical load, which is this guy, and the horizontal, that you're going to be at Moore-Coulomb failure, long before, and so the linear elastic model is not a correct reflection of the stress. It says you can stress the rock all the way from, here's your vertical load, here's your horizontal load, and it's too different. You can't support that. So you have to open your mind to different stress models. And this is the important point with, that Mark Zoback brings out, is much of the Earth's crust is critically stressed. And it can be either a reservoir rock or it can be a conventional shale. And so to elevate our game, I think we need to consider multiple failure models, because it's complicated.
No, I absolutely agree. And I've been sort of working on this, trying to figure out where you can use a strain-based stress estimate, like the poroelastic, the equations you showed, and where you need to switch to a stress-based analysis. So that's exactly along the lines I've been thinking about. The problem with the stress polygon of the Anderson, and actually Anderson did it in 1905, a bit before Mark, but the problem with that is that if you don't distinguish between lithologies, then you just always get the Moore-Coulomb friction angle, and so you don't get the sort of resolution on the stress contrast that we see when we do stress measurements. So that's the issue I'm working on at the moment. But I was keen to really see this presentation and to show the data and the processing they're showing, because that Poisson's ratio, that constant Poisson's ratio, makes no sense to me. And what we've done is, when we've done core tests with Fractech, they do confined elastic property tests, and when they calculate the Poisson's ratio from the core test, it shows the lithology difference. So there's obviously a significant discrepancy in some of these cases between what the log is showing and what the mechanical testing is showing. But it's a very good presentation. I really appreciate you giving it today.
Yeah, Tony, that's really good, you know, and you're absolutely right. Whenever you start, you know, looking at rock strength and integrating with core data, you know, with correlations and whatnot, there's still, I think that's another area that's ripe for, you know, exploration. That the issue of scale that exists and the mechanical behavior of, you know, what's the problem we're trying to solve? And quite often in geomechanics, the scale of the problem we're trying to solve is much larger than the core data. And thanks for your kind words and whatnot. And there's still plenty of things to work on.
I know we have a few more questions, but I'm going to have to bring this to a close. And Tom, I mean, you can see by the questions that you really got people intrigued, and a tremendous clear and provocative presentation. Thank you so much.
Okay, thanks, John. And my email is just tom@tombrattonllc.com. I'd be happy to answer any questions.